Yeah, welcome everybody. Thank you, Mr. Schulz, for the nice introduction. Welcome everybody to my webinar. I have to admit that this is my first webinar I'm holding, so I had some problems with the techniques, but I hope I can learn more. I see a lot of friends already signed in for the webinar, already being quite familiar with metal organic frameworks, but I see also some newcomers in the field. I would like to start, so this is an overview about metal organic frameworks essentially, and the reason for giving such a webinar is actually that DECHEMA has within the last years monitored a little bit the activities of metal organic frameworks in Germany, but also in the whole world. And we were sort of sitting together in a group and trying to find out where the metal organic framework research could go and what are the main fields. So this presentation is sort of a mixture, I have to say, of own results, but also tries to reflect a little bit what is state of the art in the MOF research, and especially we were also trying to monitor where metal organic framework research with respect to industrial research and industrial applications could end up or go for. So please, can you go to the next slide? Yeah. So a little bit on the history and on the background, how this sort of process initiated. We founded a sort of so-called temporary working group within the DECHEMA organization. Now almost 3 years ago, in 2012. These temporary working groups are basically initialized in order to identify new areas and to see what is the need in research and in cooperation between industry and academia. So in this respect, we gathered a community of about 15 people who were involved in this temporary working group, and you see also the web page is also on the bottom, is also announced. It's a little bit complicated web page, but you can also take a look at it, and in principle you can also become a member if you're interested. Just send me an email, and then you may also be interested to become a member of this temporary working group. And essentially we were doing several workshops in Germany, but in the end, in 2013, we organized a road mapping workshop together with industry and to ask what are the expectations from industry with respect to, let's say, new porous materials as metal organic frameworks are. And from that on, we evaluated this. This was a workshop with about 50% contributions from industry, but also from academia, from research institutes and universities, mostly in Germany. And from that we were sort of designing a roadmap. And this roadmap is now, at the moment, unfortunately only in German available, but this will be also the next step that we translated. So this roadmap, you can see yellow highlighted on the bottom, is now available online, and it tries to summarize a little bit what are the expectations and the fields in the future for metal organic frameworks, the way the DECHEMA sees it and the way we see it. So can you go to the next slide, please? On slide number 3, you see the organization of my presentation. So for those who are not so familiar with metal organic frameworks, I have some introductory slides telling what are the properties of metal organic frameworks, what are their structures like, what are the typical features. And then in the second part of the presentation, I will highlight some examples of what they are good for and what they could be good for in the future. And from that, I will try to draw some conclusions on the research needs and also the improvements that have to be addressed essentially in the future. So next slide, please. Yeah, slide number 4. So this is really why MOFs are exceptional as compared to other porous materials. They are outstanding with respect to specific surface area. They can reach specific surface areas up to 6,000 or even 7,000 square meters per gram. You can see that on the right-hand side. MOF 210 and MIL 101 are the typical names of these record porous materials, extremely high inner surface area. and also outstanding as compared to carbons and zeolites, the traditional porous materials, with respect to pore size. Here it is also possible to achieve well-designed pore sizes which are in the nanometer regime, 2, 3, or even 4 nanometer in diameter, and this is what makes metal organic frameworks special. Next slide, please. Yeah, and this is possible due to the unique architecture. The unique architecture of metal organic frameworks is that it uses basically a node and linker concept. The node, you can see that on the left-hand side of the slide, the node is always an inorganic subunit. For example, here the well-known example from Omar Yagi, who is one of the pioneers in this area, the zinc 4O cluster as observed in MOF5, which is connected to a very simple organic ligand, a carboxylate. Here it is a dicarboxylate, terephthalic acid. And in this way, since this inorganic unit can connect to 6 of such linkers, it is possible to use the inorganic subunit as a node. So here it is, in this example, an octahedral node, so the organic linkers are pointing towards the corners of an octahedron. And this makes essentially the linking, the node concept, while the linker is typically a bifunctional or trifunctional linker, and can be used to extend and to link together the nodes into 3 dimensions. So in this way, a very highly porous architecture is achieved, and this was one of the breakthroughs in metal organic framework chemistry, because here for the first time, a surface area of 3,000, 4,000 square meters per gram was achieved in MOF5, and this was more than in traditional zeolites and even activated carbons. Next slide, please. And yeah, and this is a sort of modular concept. We can use different inorganic nodes. Here on the left-hand side bottom is the zinc 4O cluster, the octahedral node, but also very common is the pedal wheel node. You can see on the upper left part of the slide. Here 4 carboxylates are connected to 2 metal ions pointing towards the corners of a square. So this is a square planar node that is also quite often used in the metal organic framework chemistry. But I have to say that at least 20 to 50 different nodes are known depending on the metal, depending on substitution, and this is a modular concept, as well as the linkers can be chosen in different geometries and different numbers of linking sites. And here, for example, tricarboxylates or extended linear carboxylates, and in this way nowadays more than 10,000 metal organic frameworks are known, and this of course is also one of the difficulties in selecting which one is the right metal organic framework for my application. So in the next slide I show a metal organic framework that has been very early discovered, the HCUST1 structure, or this is also commercially available from BASF, the basolite structure. This is nowadays a very common MOF material, about 1,500 square meters per gram surface area, medium-sized pores. It's a hydrophilic MOF material that is quite useful for a number of applications, because it is also open metal sites and can absorb different type of gases. But nowadays we can achieve much higher surface area, and the next slide shows one of the recent examples from my group. That's on the next slide, which is the DUT-75 and DUT-76. Yeah, we call our materials after the university, Dresden University of Technology. This is this local patriotism associated to the MOF researchers, and this is a material that we discovered recently, which uses now these square planar pedal wheel units, as you can see on the left upper corner A, and these square planar units are now connected with a somewhat bent carbazole type linker to form metal organic polyhedra. So these metal organic polyhedra shown in A resemble a pore on its own. It's one pore basically and not connected yet, but we designed here a concept where the carbazole nitrogen, which is marked in blue in the figure A, basically can be used to connect now via a secondary square planar node unit these metal organic polyhedra. So you can make a porous material out of metal organic polyhedra, and this creates additional large, huge pores, and this creates a very high degree of porosity. And in the next slide, you can see some of the physisorption data on the right hand corner, right bottom. You see the typical nitrogen absorption isotherms. Here we have achieved record, a very high BT surface area, 6,300 square meters per gram surface area. Also a very high pore volume, 3 cubic centimeters per gram for the DOT 76. And you can see that for DOT 76, the large pores, the cubic pores, which are shown in green, are 27 angstrom in diameter, so almost 3 nanometer in pore size. And of course, these materials are crystalline, so all pores are very well defined, with well-defined accessible sites. So this was a recent example from my group. I have to say that our materials are not the record holders, but on the next slide we see the record holding materials as published by some other groups from Northwestern University, with the record is currently 7,000 square meters per gram, extremely high specific surface area. But you see also that there are some very complicated ligands and linkers here involved, but you can achieve extremely high specific pore volumes. And we call these materials now ultra-high specific surface area MOFs, or ultra-high porosity MOFs, because the surface area is higher than 5,000 square meters per gram. Now, I'm often asked, is this a real surface area, or is this just fake or an error in measurement? And on the next slide, I will try to address this problem a little bit. It shows basically, and here the work from Tina Düren was extremely useful. She has developed a theoretical method that basically uses a nitrogen molecule and rolls it over the inner surface area. So in this way, the accessible surface area can be calculated theoretically, just by from the crystal structure, from the geometrical van der Waals radia, and so on. The theoretical surface area can be calculated, and it shows that the surface area here is 4,600 square meters per gram. So it is a real geometric accessible surface area. And what we find in experiment, and this needs a longer discussion, of course, that if we apply the DET method, which is very well known in the community, in the right way, that is, there are some special rules, and we have published this in one of the slides. I also have the publication how to do this. If we do this the right way, we can measure a BT surface area, which is also close to the calculated accessible surface area. However, one has to say that physically the BT surface area has a different meaning, so it is like an effective absorption area. No matter, the geometrical model shows that these are real geometric surface areas. Okay, on the next slide, I show that nowadays many porous materials were discovered. I just want to highlight that here people have now discovered also high throughput methodology that allows you to extremely rapidly check if a new material, a MOF, is porous or not. This is just one example. For example, from Rubotherm, they have developed a 12-port measurement system which allows to measure 12 samples in 5 minutes with a special technique, so-called infrasorb technique. But also other researchers have contributed to new high-throughput testing methods that allow nowadays to very rapidly discover new and highly porous metal organic frameworks. And this also creates some problems, because as you can see on the next hand slide, this is only a collection, but now we have a high multitude of metal organic frameworks, lots of different structures that are quite complicated, and for industry, of course, one of the questions is which one is the right one. We have different properties. It is not even possible to say this one is stable or a MOF in general is stable or unstable or has a catalytic property. It very much depends on the metal that is used, the linker that is used, and as I said, more than 10,000 structures are known. Talking about stability, on the next slide you can see also that recently zirconium MOFs has been developed. Here I should also say, of course, that the most well-known metal organic framework made of zirconium is UIO 66, which is the zirconium MOF, and here we show also some metal organic frameworks that were developed in Dresden. And the only thing I wanted to show is that if you choose the right synthesis and if you choose the right concept and right metal, then you can have very highly chemical stable also materials, which is, for example, this zirconium MOF, which is also stable in concentrated HCl and doesn't dissolve. Okay, so this was more some introductory remarks on the structure of metal organic frameworks. But on the next slide, I will go more into the question how to industrialize metal organic frameworks. And of course, the first question we are always asked is, what is the price of a metal organic framework? And here you can see a little bit the historical development. The first highly porous metal organic frameworks were discovered in the late 90s and basically on the milligram scale. So it's a bit meaningless to talk about cost because people were mostly interested in single crystal structure analysis. Some people only collected a few crystals that they put into their microbalance and measured a high surface area, and this was already a good paper, but price at that point didn't play a role. In 2000 to 2010, some companies, especially BASF, at an early stage started to develop materials and to upscale. Of course, here it is difficult to get official numbers for price, but I would say at that point people started to make gram amounts in laboratories, in research institutes, and I estimated a price that at that time approximately a MOF would cost 100 euro per gram. Now we have the second decade in the 2000s, in the 21st century, and now people are approaching the kilogram range. So I will later also, in the next one of the next slides, I will also show that there are already some companies offering metal organic frameworks. I would say also BASF is mainly producing on the kilogram side, even though I don't have any official information from that. But I would say in general, companies, of course, companies are offering metal organic frameworks on the kilogram scale, mostly below 10 kilogram. And now we are talking about a price of about 1,000 euro per kilogram. This is of course not the Aldrich price. Aldrich is much more expensive. But this also addresses a little bit the point for the roadmap, and what we are targeting here is also that this is still a bit too expensive. It's not several decades away from the realistic price, but I would say as soon as we approach a price which is below 100 euro per kilogram, it becomes more feasible. And I think this is mostly a matter of scale. Of course, some materials are very complicated. They have ligands which are expensive and so on. And it is an interesting point to note that in most of the cases, the ligand is more the cost-producing component, less than the metal, if we are not talking about very precious metals. And so I'm very confident that in future we will reach a price which will be below 100 euro per kilogram. But of course, then also someone has to take the initiative to produce this at a larger scale. And of course, this only makes sense if someone needs such a larger scale. And this is a little bit also the hen-egg problem in the MOF development. So on the next slide, for the people who are newcomers to the MOF area, I would like to advertise some of the more cheaper and stable MOFs, which are not so complicated in structure. MIL 101 and MIL 100 are structures developed by the group in Paris, by Material Institut Lavoisier. Then I mentioned already the zirconium MOF on the left bottom side. I have put this slide together because these MOFs are relatively water stable, air stable, and have a good stability. The copper BTC, which is on the bottom of the slide, has intermediate stability. It can be, if it is kept relatively dry, then it has a long-term stability as well. Then I want to highlight also the aluminum MOFs. So very cheap aluminum-based materials are nowadays available. Fumarat from BASF also, and then the ZIF-8 is a zinc imidazolate. This is an interesting material which is also has been used quite frequently, but it is a special material because it has very small pores and it is more hydrophobic. And on the next slide, I've summarized the state of the commercialization of metal organic frameworks. As I said, BASF has relatively early started to scale up metal organic frameworks, and you can find also videos on YouTube by BASF showing trends towards the use in the gas storage area. I will show this later. But one can also recognize that small companies and also the specialty chemical producer like Strem, Merck, and so on have started to offer MOFs in smaller amounts. We see some startup companies, Fremagy, Newmat Technologies, Enovex, and of course MOF Technologies in the UK. And also Materials Center Dresden is an internal profit center which offers metal organic frameworks up to an amount of 10 kilogram, which you can use for R&D purposes. So this is my statement on the status of commercialization. And on the next slide, I will now start basically with the what are they good for, or what could they be good for, the metal organic frameworks. What is that very high specific surface area? What could it be good for in the future? So we have a lot of work in the area of gas storage and recently also heat exchange. So heat storage has become a very active area. There is a lot of literature in separation, large-scale separation or gas phase separation, but also chromatography. Biological applications have been studied, and then sensing is an area that has also come up in the last 10 years or so, and of course catalysis in the last. So on the next slide, I will show one of the early drivers of the metal organic framework applications and functions, and that is the natural gas storage. So metal organic frameworks can store natural gas at room temperature. So you can see on the right bottom basically the advantage of a MOF-filled cylinder as compared to an empty tank system. You can increase the storage capacity by a factor of 2 to 3 as compared to the empty tank system. And the reason that you can achieve a higher storage capacity is that basically the MOF assumes a higher density in the pores. It's a liquid-like state, essentially, so a higher density, and this is the reason why you can achieve a higher packing density of the gas and a higher capacity. And this is a topic that has recently been quite interesting, especially in the US, where the shale gas has boomed. Now, I made this slide, I think, several months ago. Now we see already that the shale gas has some problems because oil has become very cheap. But we will see what the future will bring. But the message is that in an intermediate pressure regime, especially at about 50 bar, a MOF can be quite useful to enhance the storage capacity of a tank system. And in the next slide, I show one example of a porous MOF, which is also synthesized in Dresden, DUT49. It is also synthesized from a metal organic polyhedron using, again, the square planar nodes connected by the carbazole linker, as you can see on the middle and the upper part of the slide. And these metal organic polyhedra are connected into a three-dimensional porous structure with very large pores up to 2.6 nanometer in diameter, almost 5,500 square meters per gram surface area, and this material is currently the not only the gravimetric storage capacity is essential, but also the volumetric, and for this point, of course, other materials may be also quite interesting, so it depends also what are the preferences in the application. So in the next slide, I show an application that is not from our research, but from the research of the Fraunhofer ISE in Freiburg by Dr. Henninger, and this is also has become also a very active area using porous materials for heat storage. Essentially, this is used as a heat pump. Typically water or alcohols are absorbed, and when they are absorbed, the absorption heat is released. And the drying and the absorption of the heat can be used for generating heat pumps. And MOFs are outstanding in this respect because they have a very high capacity for water absorption, and this results also in a very high jump and a very high absorption heat. And this is one of the benefits here. Here you can see also that in developing products, it is now probably not the question how to make a new metal organic framework, but how to generate a structure, a morphology, or a formulation that allows to receive the optimal performance. For example, here this is a MOF-coated heat exchanger by Dr. Henninger, where the metal, which is of course important for the heat transfer, was directly coated with a metal organic framework, probably a copper containing metal organic framework. And here you can see that going into product development, we have to focus also on shaping technologies and coating technologies. On the next slide, you can see some of the benefits of metal organic frameworks. Here it is really the tunability. Metal organic frameworks can be tuned in terms of hydrophobicity, hydrophilicity, that is the water uptake and at which relative humidity the water uptake starts can be tuned. And you can see this here for an aluminum-based mill and for an iron-based mill. They have both very high adsorbed mass and water uptake, here almost 78%, so very high water uptake, but it is also possible to tune the hydrophobicity. And essentially for the heat pump, it is necessary because you want to pump between two relative pressures, two humidity levels, like a high humidity level and a low humidity level, so that you don't need too much energy to desorb the water again. So for this sort of stepwise water absorption isotherm is extremely beneficial. Of course, in this type of application, durability is the key, and the next slide shows the durability test typically carried out by Fraunhofer ISE. And here the research shows that aluminum-based MOFs have a very good durability. There is still some loss of PT surface area, some loss of uptake in cycling, but the example shows that it is not hopeless, and the benefit is really the high capacity and the tunability of the water uptake that MOFs can provide. So these both were two examples where we think the future research in the energy storage has to be focused further, energy storage of carrier gases and energy storage in terms of heat storage. So I will further go on in the next slide with some other applications or potential applications, for example, MOFs in catalysis. I should say that there's a wide variety of research results in this area already, also by other contributors. We have relatively early used metal organic frameworks as supports for metals. Also the Fischer Group has done this using some other methods, but here we show, for example, early results on using a Mill 101 structure, where you very easily can use an incipient blackness impregnation to generate palladium or platinum particles inside the porous system. And these catalysts have a very good performance, for example, in hydrogenation reactions, like you can see on the left-hand side, styrene hydrogenation, but also in cinnamic acid ester hydrogenation. So very high activity. And in the next slide, we can see that only possible to use the metal organic framework as a support for metal particles, but you can also, and this is I think the power of the MOF concept, you can also integrate active sites. For example, here we've integrated some rhodium type pedal wheels that show intrinsic hydrogenation activity, for example for hydrogenation of styrene, and this is of course one of the benefits that you can integrate also intrinsic active sites. And nowadays a wide variety of catalytic reactions have been reported, not only hydrogenation but also Lewis acid catalysis, alkylation reactions, and I don't have the time to go in detail, and I would also like to refer on the book by David Farossin on metal organic frameworks, which has a chapter in this area. Let me go further in the next slide. I'm going now from catalysis away to separation, because in catalysis we have many competing materials with long durability and stability, so I think this is probably the farthest away from commercialization, while in the separation area, especially the gas separation, a lot of studies have been performed really showing outstanding properties of metal organic frameworks. For example, the CO2 separation area has been extremely active, especially in the States, where carbon capture programs were very active in research, and people nowadays have a good picture of which metal organic frameworks has good selectivity towards CO2 adsorption in the presence of nitrogen. This is not so challenging actually to find a good separation material to separate CO2 from nitrogen in dry air, but it is more challenging if you have a presence of water or other trace gases like sulfur oxides, SO2, SO3, and so on. And this slide here, I've also cited the review on the bottom, is a newer review on separation applications, showing that nowadays also MOFs are available that have a good tolerance towards water because they are very hydrophobic, but still have a good selectivity for the capture of CO2. And while the carbon capture and storage, in my view, is still a little bit further away from any commercialization, because absorption separation is very demanding for these large amounts. I think biogas upgrading separation of CO2, for example, from methane, is probably more a direct target that can be looked at too. Or what is also an interesting target are specialty gases like SF6 or CF4 that are used by the semiconductor industry, and these have an even higher global warming potential as compared to CO2, and are still emitted from the semiconductor industry. And this would be also an interesting product for integration, because here we are talking about a small-scale development in the beginning, and there it is maybe easier for market introduction. On the next slide, one can see that shaping of metal organic frameworks has also had a lot of progress nowadays, especially for separation applications. Of course, you can do separation applications in a breakthrough experiment, in a adsorber bed, but the other way to do it is essentially using membrane technology. And here I refer to the work of Jürgen Caro, who has developed quite selective membranes, for example, for hydrogen separation, using ZIF materials, ZIF7 in this case. And nowadays it is possible to form membranes on certain support materials, and crack-free membranes are available. And this could be interesting for these more simple gases like hydrogen separation, but people are looking now also into, and this shows the next slide, into, for example, propene separation. That's on the next slide. And here also ZIF8 has quite a good selectivity, this time not because of the thermodynamics of adsorption, but due to the kinetic separation, because the propene is somewhat a more lean molecule which can easily and quickly enter the pore system, while the propane is a bit more lazy, and in this way a kinetic separation is achieved. And On the right-hand side, you can see that separation factors up to 50 have been reported in membranes, and this is quite a good result. It's better than the zeolite results, significantly better than zeolite membranes, but there are also some carbon membranes in the literature that have somewhat better performance. But it shows that it is possible to integrate such materials into products for beneficial separation. And on the next slide, I show also, I think this is a very active area at the moment, also the development of polymer membranes, mixed matrix membranes. Here, this is a slide from Fraunhofer IGD showing MOF additives in polymer membranes. And of course, as compared to the pure inorganic membrane, this has the benefit that it's just cheaper in conception. And here there's a lot of active research in developing tortuous structures, as you can see on the right bottom part of the slide, where high selectivities have been reported with layered metal organic frameworks materials integrated into porous MOF membranes. So this is still under development, but I should say that several companies are also active here in the development, and we will see what future developments will bring here. Very early on, and this is on the next slide, thank you, it was already shown that MOFs can be used also for trace gas removal, trace impurity removal. For example, in gasoline or in general in feeds, often sulfur compounds are a problem for catalysts. And some of the MOFs have very high affinity towards sulfur compounds because they have these active metal sites, for example in HCAST1 or MIL101. And on the right-hand side, this is from Müller's publication from the BASF, showing that you can achieve a very good removal for example, for model thiols, tetrahydrothiophene, which can be removed quite efficiently. And I think this is also one of the strengths of the metal organic frameworks, that they can be used for selective removal of certain toxic or not wanted gases in a gas stream. And this is shown also in the next slide, where you can see an example for tick removal. Tick are toxic industrial chemicals. A typical example is ammonia, which is still used in chemical industry to a wide extent, or also even in cooling applications. It's quite common for ice cooling engines, and also for heat pump machines, basically. Therefore, it's a certain hazard. And here we show that the MOF significantly outperforms activated carbons. This is also a breakthrough curve with almost 2 hours holding time for the breakthrough, and a very steep curve as compared to the activated carbon, and showing that this is also very effective for the toxic gas removal from air, for example, from air applications. Going more into special applications and fine chemical separations, chromatography is also an interesting area. One has to say that at least 50 publications nowadays report the use of metal organic frameworks as a stationary phase in a HPLC column, for example, or also in a gas chromatography column as a thin surface coating. And people have reported that these MOFs can be used for separation of permanent gases, small molecules, but also in HPLC applications for the separation of larger fine chemical molecules. And people have even reported that the MOFs can be enantioselective, so to separate chiral analytes, essentially. So at least 20 publications are seen in the literature where enantiomers are successfully separated. This is just one example where we have developed an enantiomerically pure metal organic framework with a functionalized linker, which shows a reasonable separation of 2 enantiomers. But one has to say that the strength of the metal organic frameworks is that they are specific towards a certain molecule, and not so much can be used for general application and to separate quite a variety of molecules. I will finish the application part basically with two examples showing recent trends, for example, in the area of luminescent MOFs. Here, the porosity is not the key feature, but people have integrated lanternides which show strong luminescence and can be used as converters, for example, for white light emitting devices. This is a quite recent area. Here, the porosity could play a role in terms of lensing. If a molecule is absorbed, the luminescence changes. This is also an interesting phenomenon, but not so much explored yet in commercial applications. But this is also an interesting feature of metal organic frameworks. And the last slide in the application part shows the general phenomenon or the general trend in the area of sensing. People are using metal organic frameworks for gas sensing. This is an example from Allendorf and co-workers, where metal organic framework was coated on a cantilever, and then essentially the signal was read out depending on the water humidity. So this is essentially a moisture sensor. I think this is only a proof of concept, but of course, when you design a metal organic framework with a high selectivity and recognition character for a certain molecule, then this becomes very interesting and competitive as compared to other sensor systems. And thinking about product integration, also the advantage is that here we need only very small amounts, so the price of the metal organic framework itself is not as decisive as compared to the system cost. So with this, I will close the application part, and in the last, in some two slides, I would like to highlight and point out also that whenever we talk about functions and applications and industrialization, the shape is very important. In most of the cases, the powder cannot be used for the application, but we need some sort of formulation. And this can be either a monolith, for example, shown on the left-hand side, one of the early examples of a monolith, but also Fraunhofer IKTS is providing monoliths that can be used, made from metal organic frameworks, but also granules as provided by the Material Center Dresden. You can see on the right-hand bottom part. And all these technologies are important for product integration. And I could probably give more examples. I have only one more example in the next slide, which shows an example for a fiber integration. For example, for air filter applications, one is interested in a textile type metal organic framework. So metal organic frameworks have to be integrated into very thin textiles. This is some early work that we did on electrospinning for air filter applications, electrospinning of metal organic frameworks. And here, of course, the key is to integrate the metal organic framework in a way that the properties are retained, the high specific surface area, the accessibility, but we receive a permanent structure which is easy for handling and can be used. Okay, so when we summarize these type of applications, and this was part of the things that we did within the road mapping process, we were trying to find out what are the applications that are realizable in a short-term sense, let's say below 5 years. And here we have identified areas which are, and I've given some examples already, with low technology risk. That means that the technology is already developed at a high readiness level, meaning that only minor developments have to be carried out, and also in this sense the economic risk will be low because, for example, for sensing or maybe also for air purification, it is not necessary to provide tons of MOFs, but also to provide maybe kilograms of MOFs. So this can be a good interesting starting market, or maybe even also as a guard bet. Then in the separation and in the energy area, it becomes more complicated. This is this blue bubble. The bubble size was here meant to essentially give the market size or the potential market size. This has, of course, a larger market size, but also for separation, larger amounts, and formulation has to be developed, stable MOF granules, and so on. And so we see here a higher technology risk and also a higher economic risk because of the investment in upscaling technology. And this refers to energy and separation. And the catalysis part, the red bubble that was on the previous slide actually, the red bubble on the Mr. Hoy, can you go? Yeah, the catalysis part we see is more, in our view, is more a future development. It was interesting to see that in our road mapping workshop, nobody was interested in develop MOFs as a catalyst. Nobody from industry was interested to develop this as a catalyst. So we see this as a not mature area and probably the area that needs most fundamental research. Okay, so this brings me to the research needs slide on the next slide. The research needs that we have identified, and at the moment maybe it's not that necessary to develop new MOFs, even though this is an interesting and important task for academic research, but for the industrialization, stability is the key issue, so we need to develop more stable, chemically stable metal organic frameworks, more thermally stable metal organic frameworks. The reduction of cost is essential for market introduction, but here we think that in the future, in the next 10 years, we will see also downscaling, upscaling and coming down of the cost, especially if the needs are also there. So it's always an egg problem in terms of if there is no customer, then nobody will take the risk of upscaling. Shaping technologies are essential. And also one area that is not so well addressed yet is the toxicology problem and the REACH process. So as far as we are aware, there's no REACH regulation yet for metal organic frameworks. Toxicology has been addressed by research institutions, for example, the group in Paris, showing that some MOFs are biocompatible, especially the iron-based MOFs, as you can see also on the right upper slide, and therefore there's no fundamental issue, but it has to be taken into account in the future. And for product development, as I've shown, we see several areas: separation, gas purification, sensing, heat pumps, and gas storage, and catalysis maybe also in the future. So in the next slide, I show that I think this is also a little bit typical for this area. Metal organic framework has started from academic research in the late 90s. In Germany, a larger program with 36 groups has done a lot of fundamental studies in evaluating the properties of these materials. Many universities have good knowledge what are the properties, how these materials can be synthesized, and also what are the basic fundamental functions. But now it is, of course, the question in the future how this fundamental research results can be transferred to an industrialization. And here certainly now a good match between companies who are interested to use the technology and experts in Germany but also worldwide is beneficial in order to screen what are the best applications in the future. And on next hand slide, we show all the active partners in Germany who are active, more than 40 MOF research experts in Germany. And as I've said, in the roadmap you will find also the exact addresses. So if you are located in, let's say, Berlin, and you want to discuss a potential application with a MOF expert, you can contact the contact who's named there, probably Arne Thomas, or you can find it in the roadmap, or also Professor Holt in Potsdam, which is close by, just giving an example. And I will show in the next slide again the web page for the roadmap. This is on the next slide. Again, if people are interested to download the roadmap, here also all the experts are named, and you can find the addresses. And if you are interested in more information about metal organic frameworks, of course, you are all invited to join also the first European Metal Organic Framework Conference in Potsdam, close to Berlin. And this is my last slide on the announcement. So this will take place in Potsdam. On the last slide, you can see the announcement. Genau. Yeah, that's it. So if you're interested to join and discuss with the experts in this area. So thank you for your attention. I should thank also all my co-authors and the organizers by Decima. On the last slide, I have also an acknowledgement, transparency, because we receive also funding from various organizations. BNBF, especially the DFG, was very helpful in also supporting all network activities and establishing quite a high knowledge in Dresden. And with this, I would like to thank you all for your attention. Thank you very much for listening.